All right, welcome back everybody. So we are going to look at the ratio test today as kind of a supplemental here, and we'll prove why the ratio test is going to give us our three possibilities here, which is the absolutely convergent series, the divergent series, or an undetermined series outcome. So we'll just recall that the ratio test says, suppose that we have an infinite series, an, and we let L equal the limit as n goes to infinity of an plus 1 over an, so the next term divided by the previous term. Then if we get L is less than 1, then our series will be absolutely convergent. So absolutely convergent is where the absolute value of our series converges. So we make everything positive term by term, and we still get convergence, and absolute convergence implies regular convergence as well. So if we have an absolutely convergent series, if the absolute value of the series is convergent, then the series itself is convergent. And then if L is bigger than 1, then our series is going to diverge. And if L is equal to 1, we could be divergent, we could be absolutely convergent, or we could be conditionally convergent. And conditionally convergent is typically going to refer to some sort of alternating series example. So let's go ahead and get through the proof here. So again, we're going to make those first two assumptions. We've got an infinite series, and we have L defined as this infinite limit. So we're just going to go through each case. I think we'll start with 3, and we'll just do this by example. So we can look at convergent series that we know we'll get L is equal to 1 when we take the ratio test, and we'll end up with these 3 different possibilities. So the first one is going to be P series, and we could take any P series we want, but 1 over n squared is probably the easiest one, and this is going to be absolutely convergent. But if we do the ratio test, we end up with a value of 1 for L. And note the P series test we can prove using the integral test. So that is going to be absolutely convergent. If we want divergent, we could use our harmonic series, of course. So again, we'll get L is equal to 1, and we know that our harmonic series diverges. And then finally, we'll take the alternating harmonic series, which is conditionally convergent, right? So this series converges by the alternating series test. So we can use the alternating series test to show convergence. But if we take the absolute value, we get our original harmonic series. So this is going to be conditionally convergent by the alternating series test. So these are 3 examples of when L is equal to 1, where we get these 3 possibilities. So next, we'll go in reverse order here. So we'll go to 2. So we'll want to prove that if L is greater than 1, we will diverge. And what we want to ensure here is that when we're considering this value of L and this limit, we want to be kind of far enough out in the series that we're not kind of near 0 or near 1 or 2 or 3. We want to go far enough out where this is going to clearly denote the behavior of this ratio of these 2 values. Because certain series can start with really big numbers that shrink. So if you compare those really big numbers, you might not get this. And again, we're taking the limit as n is going to infinity. So we want to make sure that we're considering values really, really far out. So we'll suppose that L is greater than 1 for this case. So thus, for some n. So we'll say for some n greater than or equal to some capital N. So that's going to be some term out in our series that is far enough out that such that we'll get a sub n plus 1 over a sub n. The absolute value is greater than 1 for all. So it might not be greater than 1 for, maybe the first 100 terms or the first 10 terms, but this is going far enough out where it will always be greater than 1. So we can take our absolute value inequality here and we can manipulate it a bit. So we'll note that this is going to be the same as saying that a sub n plus 1 is greater than a sub n in absolute values. But if the next term is bigger than the previous term, this means that the limit as n goes to infinity of our series is not equal to, of our sequence, is not equal to 0, right? So in order for our sequence to shrink to 0, it's got to be getting smaller in terms, but this is indicating that the terms are increasing. So if the terms are increasing, the limit here is going to be not equal to 0, which also means that the limit as n goes to infinity of a sub n is not equal to 0. Okay. So this means that our series diverges. So essentially, if it's bigger than 1, you're going to end up with the limit of the sequence not going to 0, which is required for all convergent series. So if a series is convergent, the limit of its sequence has to go to 0. All right, so now we're ready to get into the most important part, which is proving that we are absolutely convergent if L is less than 1. So we'll suppose L is less than 1. Thus, there is some value R such that L is less than R is less than 1. So we're going to pick this value of R between L and 1. L is clearly smaller than 1. R is going to be some number between L and 1, but it's fixable, so we can move it kind of anywhere we want. We can make it really, really close to L. We can make it close to 1, but it's this flexible term, and we'll see that the reason why I'm using R here is because we're going to end up building a geometric series. So this is going to be like our common ratio of the geometric series. So there's this value of R and since we know that L is equal to the limit as n goes to infinity of a sub n plus 1 over a sub n for some n greater than or equal to capital N. So we're going to go somewhere far out in our series so that we end up with this value being really, really close to our limit of L. We have a sub n plus 1 over a sub n is less than R, because we know that it's approaching L, and L is some number smaller than R, but it is positive, so it is greater than 0. So L has to be a positive number, R has to be a positive number, but if we go far enough out, as our limit of this ratio approaches L, at some point it's going to pass R, and it's going to be smaller than R. So this will be true for some n greater than or equal to this capital N. So again, this is just far out in the series? Sequence. So this is just some really big number way far out in the sequence, such that this will be the case always. So now we can again do a little bit of algebra. So we get that a sub n plus 1 is less than r times a sub n, again all in absolute values. And now we can begin to construct an argument. So where we're looking at these values where again n is greater than or equal to capital N. So noting this, we can start constructing statements like a sub capital N plus 1. So this specific term in the sequence, as opposed to just some nth term in the sequence, well, this is going to be smaller than r times a sub capital N. Right, so we know that n is greater than or equal to n. So if I go one term past capital N, this will be true. And then I can now say, okay, well, what if I go two terms past? Well, a sub n plus 2 is going to be less than r times a sub n plus 1, which is in turn less than r squared a sub capital N. And then we can continue on. So we can do the third term past n and construct the same sort of argument. And note, this is going to hold because r is smaller than 1. So these powers of r are going to continue to shrink our values. And we also know that the ratio is going to be less than 1. So a sub n plus 1 and a sub n are going to be smaller. But these cubed, squared, and r terms are going to guarantee the inequality here. And we can kind of continue constructing this so that for, let's use k maybe. So for k in the counting numbers, we'll get a sub n plus k is less than, and the parts that we're interested in here are actually on the ends of the inequality. Oops. Right, so we've got r squared, r cubed times a sub capital N. Oops. And so for the n plus k term, so k terms past that capital N value, we'll get r to the k a sub capital N. So this will hold in general that the n plus k term of the sequence is less than r to the k times a n. Oh, again, still in absolute values. So that's kind of interesting because what we've just constructed on the right is a geometric series. So what we'll notice here, that the that if we fix this a capital N term, because that's just a constant number, and we have that as our leading term here, times r to the k, this is a convergent geometric series. Since r is going to be between 0 and 1. So we got this convergent series, and we've got that the n plus k term of our sequence is smaller than that. So that's going to be very useful because that means now we can use like a comparison test. So what we'll note here is that we can rewrite our series in a particular way. So if we took the series from the n plus 1 term to infinity, that's the same as, that's the same as saying k equals 1 to infinity of a sub n plus k. So we'll just note kind of a convenient shift in our values here. So if I take the infinite series starting at capital N plus 1, so I start way, way, way far out, and I go to infinity, I can rewrite that in terms of k, where k is the kth term beyond the capital Nth term. And so this is kind of the series that we want, because this is the series we're considering here, right? So we want this capital N plus k to be written as a series. So note, it is the same as this original series that we started with. So this is our very original series, but not starting at 1. So instead of starting at 1, we're going to start at capital N plus 1. So we've got this convergent series here. So we'll say by the comparison test, and again, we're going to use our inequality here. The sum k equals 1 to infinity of a sub n plus k is less than k equals 0 to infinity of a sub n r to the k. So that's by our comparison test here. So we know that the series a sub n plus k is going to converge, and it converges absolutely. So we'll maybe make a note here. This is an absolute convergence, which is absolutely. So that's nice, because now we can finally just get to the convergence of our original series. Thus, the original series that we started with, a sub n, if we take the series, the sum of the series as an absolute value, that is going to equal well, we can split our series up here into two pieces. And we'll note this first part of our series is just a number. So note this is a finite, this is just a partial sum. So that's a finite number, and this series was the series we just discussed, converges absolutely. So note this series is equivalent to this series. So that was kind of this statement over, what the statement over here was for. So that part converges absolutely. So if we have a finite sum, that clearly converges. Plus this infinite sum, which we know converges absolutely. Well, the sum of two convergent series is also convergent, and both of these converge absolutely. So our original series converges absolutely. So a little bit of construction required for this. So we kind of had to set up this inequality argument, but it's pretty straightforward. And what this guarantees is that our ratio test will be true for these three conditions. So if L is less than 1, the series will converge absolutely. If L is greater than 1, the series will diverge. And if L is equal to 1, it'll be inconclusive and we'll have to use a different test. All right, so just wanted to go through a quick proof here of the ratio test. Hopefully it is helpful, but if you do have questions, definitely shoot me an email or come by my office hours and we can discuss it more. And until I see you next time, take care.